I request Dr. Rishi Asthana to be our session chair for the next one.
Thank you. Good noon, everyone, and welcome to the session. I invite Mr. Sagnik Saha to deliver his talk on the generalized Fermat's polygonal number theorem.
Hello. Yeah. So, firstly, thanks a lot for giving me the opportunity to speak at BRICS. I'm really pleased to talk in front of such a great audience and in such a great conference. So, for today's talk, what I'll mainly do is present some of the results that are generalization of the Fermat's polygonal number theorem. So this is a joint work with the summer research group that was headed by Dr. Benjamin Kane, and we were a team who worked for 2 months in summer. So this will be the structure of the talk. So I'll firstly start with some history as well as some early work, and then I'll move towards the main theorems after mentioning some lemmas. Okay, so firstly, before going to the main part of the problem, I want to mention a bit of history. So a lot of you might have seen this book cover before. So this is the cover of the original 1621 edition of the Arithmetica by Fermat. And this has been a great deal of inspiration for Fermat for a lot of his problems and his work. And it is very well known as a myth. As a story that Fermat used to add notes to the margins of this book, and that's from where the last theorem and the story behind it came. And this is a reprint 1670 edition of the same book, along with Fermat's notes. So the last theorem wasn't the only thing that Fermat noted down inside that book. There are many other conjectures and problems that he wrote down but didn't give a proof of. So one of that is today's discussion. So before going into the problem part, let me define what polygonal numbers are. So polygonal number, or we'll call as a part of this talk an m-gonal number, is a positive integer which can be represented by a regular polygonal arrangement with m sides of equally spaced points on the plane. So with this illustration, you will be able to know more about how it looks like. So, for an example, 1, 3, 6, 10. These are all respectively the first, second, third, fourth, fifth triangular numbers. So they look like this in arrangement. And similarly, there are pentagonal numbers and heptagonal numbers, stuff like that. So there will be a formal mathematical definition for the same as well. So we define the xth m-gonal number, where x and m both are natural numbers, and m is a positive integer greater than or equal to 3 with this formula. And we will call x as the rank of Pm of x. So then we directly get the triangular numbers will have a formula of x into x plus 1 by 2. So these are very well known, as well as so the square numbers directly come as p of 4 of x, which is x square, and the pentagonal numbers come like this. And we immediately get a very nice identity which relates polygonal numbers and triangular numbers. Yeah. So I'll mention some early work that came up in this field, which motivates our present work. So firstly, in 1638, Fermat conjectured this. So he wrote again in the margins of the book that every positive integer can be written as a sum of m or fewer m-gonal numbers. So he actually promised to write an entire book on this subject, but he never did. And much later in the next century, in 1770, Lagrange proved the m equal to 4 case of the above theorem, which is known as the celebrated 4 squares theorem. So you might have heard it, like representing any integer as a sum of 4 squares. And Gauss subsequently proved the n equal to 3 case, and which is famously known as the Euler theorem, of course. And Cauchy in 1813 showed that every positive integer can be expressed as a sum of m-gonal numbers. So this is the maximal case, and we actually want to make this summation, this sum structure, a bit better than how it was originally proved by Lagrange, Gauss, and Cauchy. So there is another great theorem which uses polygonal numbers inside it. So it's the Euler's Pentagonal number theorem, and this is from where the field of Q series rises. So here the Euler function phi of Q is defined as this product function, and there is this product summation identity, and Euler proves this entire identity where we see that the powers of Q are actually pentagonal numbers. And these are not only just pentagonal numbers, they are generalized pentagonal numbers, and we'll soon come to the definition of what generalized pentagonal numbers are. So, moreover, sum of squares and triangle numbers were studied extensively after these problems, so including famous problems like the Waring's problem in the Pell's equation. And even after that, the initial problem did not end. So, Richard Guy in 1994, he posed questions on the optimality of polygonal number theorem and introduced the notion of generalized polynomials. So now we define what a generalized polygonal number P of x is. So here we just take the rank to be an integer instead of being just an natural number. So Guy also asserted that we do not need exactly m-gonal numbers. It can be done by less than m. So is the same true for any general m-gonal numbers? Can we always use less than m terms in a sum? So that is one of our motivating questions. So now we call a sum universal if we can represent every positive integer. So we ask for what minimum value of L is the following sum of polygonal numbers universal for a given m. So we generalize the previous question more, and then we consider a weighted sum. So we now define a particular vector A, and for m greater than or equal to 3, we ask what is the minimum value of L, such that this sum, where each of the Pm of xj are weighted with Ej, is universal. So there is a very interesting result of Conway-Steenberg, which is known as the 15th theorem, and then Kane and Liu also in 2019 proved some results that there exists a unique minimal lambda m, such that Pm of A, which we defined earlier, this sum, this weighted sum, is universal if and only it represents every n up to lambda m. And they further showed another bound of lambda m, which stays between these two numbers. So these bounds were further improved by Kim and Parr to show that there exists actually an absolute constant, such that the lambda m gets bounded between these two. But these are also not quite helpful, because in some cases this constant only exists for very large m, or they are not very easily computable. So for question 1.2, we consider this slightly specific case where we take some of the initial numbers inside the vector as 1 and the rest of them as r. So 1 is repeated r minus 1 times, and r is repeated as l dash times, which is this, for some fixed r belonging to n. So we can now try to find an optimal minimal choice for Lm of r, for which the sum of generalized m-gonal numbers which look like this. So we have taken the earlier sum and broken into two pieces. In the first piece, the weights are all 1, and in the second piece, the weights are all r. And we want to prove that for what conditions this is universal. And the case where r is equal to 1 is exactly the same as the statement in our initial question. So now I'll mention some our results from our work. So in the first theorem, what we do is that for all m, which is not 7 and 9, we have particular values for our L. So remember again, L is the total number of terms inside the sum, and we want to minimize that term as much as possible. And earlier results were that m was the number of terms required are exactly equal to m, but we have reduced this to m minus 4. And for if m is 3, 5, or 6, then L is equal to 3, number of terms required is 3. If m is 4 or 8, the number of terms required is 4. For 7 and 9, I'll come back to that case soon. So, and again for r greater than 7 and between m minus 3, we have this result for L, number of terms required, which is much less than m minus 4. And thirdly, the third theorem that we have is for specific cases of R between 2 and 6. So here we have taken R greater than or equal to 7. So for values of R between 2 and 6, we have certain results. Okay, so before going to the proof of the results, I will describe some preliminaries that we need. So firstly, the sums of polygonal numbers that we saw earlier, they are a special case of a natural class of functions, which are known as quadratic polynomials. So they are a bit different from something that you already know, which are quadratic forms. So a totally positive quadratic polynomial will be defined like this, where q of x is a quadratic form, positive definite, and L is a linear function defined over Z, and C is a constant. And for a totally positive quadratic polynomial in L variables, we set this following set this following number, and we first check for representations of n by a quadratic polynomial by testing it locally. And an integer will be represented globally only when it will be represented globally as well for over ZP. So this study was mainly done with Minkowski about the local and global representation. So we won't go further into that, but we will use some result by Siegel. So before that, Siegel has defined this particular summation, and so these are overall isometric classes of positive definite Qj. And we only use a special form of the result, which states that, so this is a theorem by Siegel and B. So we have R gen Q of n greater than 0 if and only n is locally represented. Moreover, is the class number of Q. So we dive a bit into classical theory and we get that if the class number of Q is 1, then RQ of n is greater than 0 if and only n is locally represented. So if our quadratic polynomial is firstly class number 1 and also represents locally, then it will also be an universal quadratic polynomial.
Sorry, what is the number of variables? Is it a binary quadratic form? Yeah.
This is a binary.
So L is equal to 2, is it? We say positive definite quadratic form. Do you mean binary quadratic form or in some general?
No, okay. So L variables. So variables will be dependent on the number of terms that we have inside the sum. Okay.
But if L is bigger than 2, how do you define the class number?
How do we define the class numbers? So that I actually don't know. I have just used a result from them, and the polynomial that we have used later on doesn't require like properties.
No, just like this. What is the number of variables in which you take the quadratic form?
So our quadratic polynomial is in L variables, where L is dependent on the number of terms inside the sum. Okay, let me just go through it and I'll come back to it. So this is the lemma that we firstly prove, which will come as come helpful for our first theorem. So we define this sum first, and we tell that it represents every integer in this particular set, which is m-2 of natural numbers. So we consider a vector in that file, and such that we have taken this specific condition on that. And for rank, for such a rank of x, we have this sum can be expanded into this, and we will see that this will automatically go to 0 because of this property. And then this particular quadratic form that we finally obtain. So this is a quadratic form with class number 1, and it represents every non-negative integer locally. So by using previous lemma, we can say that it represents everything globally as well. Alternatively, there is also a result by Bhargava and Hank, so which is the 290 theorem, and they verify that if this quadratic polynomial actually represents everything until 290, and thus it is universal as well. So now we come to the proof of our main theorem. So again, this is the statement of it. So for the case m equals to 3, it was proven by Gauss. 4 was proven by Lagrange. And Guy also uses Legendre's classification to resolve the m equal to 5 case. And again, Guy points out that the m equals to 6 case follows directly from m equals to 3 case. And m equals to 8 case was proved by Ixon. So we are taking cases where m greater than equal to 10. So since we know that this is already greater than equal to m minus 4, it suffices to prove that every integer can be written as a sum of m minus 4 generalized m-gonal numbers. So now the main work after this comes as how do we structure the given natural number so as to express it as a sum of polygonal numbers. So there is some amount of crude work here, but I will represent it in a form of algorithm. So if we have a given n and we first take it as mod of m minus 2, and then if we represent n equals to m minus 2 k1 plus k2, where k2 is in this range, then we break it into two parts and then further break it into two parts, and in each case we find out what is the minimum number of terms required so as to express this particular number n. And some of these come out directly because of some properties inside the sum. Some of them we have to hand check and make sure that every case inside this class actually turns out to be universal. So for the next theorem, we have values of r between 7 and n minus 3, and we show that what are the minimum number of terms required for the polynomial to be universal. So for r less than m minus 3, we write n in this form. So we have firstly taken mod m minus 2 and then again divided the next sum into rk2 plus k3. So now then we prove this particular lemma. So I am skipping this, and we use this particular lemma to show further that if r is between 7 and m minus 3, then there is an upper bound to the minimum number of terms required, and this upper bound is m minus 3 by r floor function plus r minus 1. Secondly, L also needs to satisfy this particular property, because we are so from there we obtain that m minus 4 is less than r plus 1 if there is a bit more computation here, and which implies there is a lower bound to L as well. And if you see that there is not much of a difference between these two upper bounds and lower bounds. So the upper bound in proposition 3.3 and the lower bound in 3.4 matches unless m divides m minus 3, because there is a floor and a ceiling function. So there is a difference only when r divides m minus 3. So we take now again two further cases. So when m minus 3 is equals to rs for some s, we know that this particular term has this form, and the claim is equivalent to proving that the polynomial is universal for s minus 1, for L dash equals to x minus 1. We have to now consider cases for k2 as well, and we use previous lemmas to prove the universality. And for example, when k2 is equal to s, we rewrite n in this form and show that it is represented by the sum when L is exactly equal to this. So for theorem, for the third theorem, we prove some special cases, and so I'll show proof of one of the case, which is r equals to 3, which is this case. So for r equals to 3, again for a given natural number n, we break the number into this part. So suppose the first part is Pm of x1, then Pm of x2, and then we take mod. We have taken mod 3, so the later part is of this form. So we use modular relations inside this with respect to 3 to arrive at the formulas for Lm of 3. So the minimum number of terms required for for r equals to 3. So since for any n in natural numbers, n is either congruent to 0, 1, or 2, we know that this sum represents every element of 3n union 0. So taking the first two elements inside be either 0 or 1, because we are taking mod 3, we get a representation of every positive integer, because this part is of the form 3n. So for m congruent to 0 mod 3, we have m minus 3 congruent to 0 mod 3, and we take n equal to m minus 3m minus 10 specifically. So note, then we will know that we arrive at this particular identity, and we get further results for Lm of 3. There is a lower one for that. And for m congruent to 1 mod 3, we take again n equals to 3m minus 12, and note that the representation of this, the similar structure that we had earlier. So that must have x1 and x2 equals to 0. So again, we get the similar lower bound for L. So for m congruent to 2 mod 3, again we do similar computations and get some results, some lower bounds for the given L m comma 3. So the techniques of these are similar. So in this part for theorem 1.1.3, all the different results that we have for several values of r are based on modular computations. And there is another variant that we also looked at where the vectors are a bit different. So here we have considered the first terms to be from 1 to r plus 4, and then the next terms. So there are r plus 4 terms exactly which have 1 as the weight, and then the rest of the terms they have r as a weight. And we show that for polygonal numbers of m greater than or equal to 8 and r between 1 and m minus 8, we have again this particular property for the least number of terms required inside the sum. So I am not proving this here. So this is also another result that we have. So yeah, thank you.
Thanks, Sagnik, for the presentation. Is there any questions from the audience? No question. Any online? You have? Yes.
Yes. Can you give them? Yeah. Yeah. So Bhargava had several papers where they work on a different kind of technique where they prove that if a particular structure polynomial represents until some number, they will represent all of that form. Yeah. Yeah. So such techniques have been used in a lot of other places, and in some cases these numbers are quite large. So if we can prove that a particular structure, quadratic structure, can represent a very large number, then it will represent everything else after that. But luckily for certain quadratic forms, they have shown that only 290 is enough, and if that quadratic form represents numbers until 290, it will represent everything after that.
Is there any question from the online audience? No? Thank you very much, Sagnik, for the wonderful presentation. Let's thank him.